Hi, I'm Jake Levinson, and I'll be presenting our work and analysis of SVD for deep rotation estimation. 3D rotations appear everywhere in computer vision and robotics, so it's not surprising that reliable and accurate rotation regression is a fundamental part of many downstream AI tasks. Rotations can be represented in many different ways. There are classic angle-based representations, which are simple but have inherent flaws such as discontinuities. Recently, a number of new representations have been proposed to fix these problems for deep learning. However, there's no consensus about which method is best. In light of the attention this topic has received, it's surprising that orthogonalization based on SVD has been overlooked. In our paper, we explore the viability of SVD for 3D rotation prediction in neural networks. Our contribution includes rigorous theoretical analysis and extensive experiments. Our results suggest that SVD is universally effective. SVD orthogonalization works roughly by scaling all the singular values of a matrix to 1. This method is at least 50 years old. It has a long history of use in computer vision and in other fields. Many strengths of SVD orthogonalization, like the fact that it is least squares optimal, have been known for a long time. Our contributions include showing that under Gaussian noise, rotation regression using SVD produces half as much error as the most similar alternative, which is orthogonalization based on Gram-Schmidt. For all of these reasons, SVD should be an obvious choice for use in 3D deep learning. However, it has been largely overlooked. To use this method in deep learning, you take an unconstrained 9-dimensional network output, interpret it as a 3x3 matrix, and then project it to SO3 using SVD orthogonalization. This layer only takes a few lines of code to implement in PyTorch or in TensorFlow. Now let's compare SVD and Gram-Schmidt. Conceptually, SVD orthogonalizes a set of vectors by moving all of them to find the globally closest orthogonal matrix. By contrast, Gram-Schmidt is a greedy algorithm, and as you can see, one of the unconstrained vectors is fixed. Naturally, this leads to worse predictions on average. We evaluated SVD on a broad spectrum of applications covering both supervised and unsupervised rotations and against many baselines. For supervised pose estimation, SVD performs best overall. When the range of viewpoints is small, hybrid classification regression methods do better, though these methods require supervision. The trend continued in the important setting of unsupervised 3D learning, where SVD orthogonalization again performs best overall. Thanks for listening, and we hope you'll consider using SVD next time you need to predict a rotation.